pleasure of being neither a student nor a postdoc of Uriel's, but I still owe a lot of my scientific trajectory to Uriel in the following sense. When I was doing my PhD, I was interested in dynamos, and I had an interest in turbulence, but neither in Germany, where I did my undergraduate studies, nor in Finland, I had sufficient possibilities to learn about turbulence. And so my first exposure to serious turbulence came at the Lesouche Summer School in '87. And I think Uriel was actually not at that school, except that he might have been visiting for a few days. But many of his disciples were at that school. And so that brought me into a light where all of a sudden I realized that a lot of the French astrophysical community is exposed to serious education in turbulence, and that is all due to Uriel's work. And so in that sense, I owe my whole scientific trajectory to much of Uriel's efforts back at that early times. Then the real exposure to him came through the meeting in Lesouche in '88, where and then more deeply in Cambridge, where there was the first Isaac Newton program on, because the Isaac Newton program school was just founded in 1992. So there was the first one on turbulence, and Uriel was there for the whole period of the half a year, maybe even, or at least 3 months, and so was I. And that was the time when Uriel wrote his famous turbulence book, the '95 turbulence book. So that was actually written while he was at that in Cambridge, and I remember he was sitting with this heavy laptop. It was not a laptop by modern standards, but a much more laptop. That was the machine that we had, and was already Linux operating and stuff, so I was quite impressed. So a lot of Uriel's early work on dynamos and turbulence had to do with helical, but also non-helical flows. And today I will be talking about something which is non-helical. And it is something which I believe Uriel had not really exposure to, because an important element in this work is the fact that we have gravity stratification. So we have non-helical turbulence, and we have gravity stratification, and we actually don't have a dynamo problem. So here's the following setup. We take a three-dimensional box of the size 2 pi cubed standard. We use an isothermal equation of state, so it's not compressible, but it's isothermal. We have, as in many cases, we have a random forcing function, which is here non-helical. We force at a wave number relative to the box wave number of 15. So that means we have some serious degree of scale separation. The box is stratified in the vertical direction. So the density then for an isothermal box behaves like the exponential of minus z over h. And h is the scale height which is given by the sound speed squared divided by gravity. So we choose units where this is 1. So that means if this is 1 and the box is 2 pi, we have a density contrast of exponential 2 pi, which is 535. So it's quite a serious density contrast already, but you can easily resolve that even with 128 mesh points in the vertical direction. Let me also remark that the scale height is constant in height. Unlike usual polytropic atmospheres where the scale height is proportional to the temperature and the temperature is linearly dependent on z, in this case it's actually constant, which has computational advantages because the computational effort in resolving stratification, of course, it comes with the smaller the scale height is. If the scale is very small, you have to have a lot of resolution, but in this case the scale height is constant, so you can get away with uniform resolution in the z direction. Use periodic boundary conditions in x and y, stress-free and perfect conductor boundary conditions in the vertical direction. So no flux can escape. Flux is conserved. We impose a weak magnetic field in the y direction. Sometimes I would call this the toroidal direction. So in that sense, again, it's not a dynamo problem. We run for very long times and ask what happens after these long times. Any suggestions yet? What could happen?
A lot of small-scale magnetic fluctuations.
Yes, small-scale magnetic fluctuations can be generated. We will run up to Reynolds numbers where the small-scale dynamo is excited. However, we also run the whole range of Reynolds numbers from below unity to up to 70. 70 in units of, or in units of the scale of the wave number at the forcing wave number. So there is either dynamo action or there's no dynamo action. Both cases are possible, but the Reynolds number becomes bigger than 1, and that is the 1 is the important one. Any suggestion what can happen yet?
It's a large scale growing, large scale
we have a large scale growing field, yes. And why?
No.
You
want me on the fly to do your work.
So when I do, of course, big scale separation, or a bigger one, of course I do ask for what happens at the largest scale, and therefore the answer was that something is ought to happen at the large scales. But first we have to find that, and in order to find that we have to run for long times, and long means many, many turnover times, and the relevant time scale is actually what I will be calling the turbulent diffusive time scale, which is based on a quantity eta sub t, which is an estimate for the turbulent magnetic diffusivity. So eta sub t is equal to, should I call it 0, because the actual one may be slightly different, is the RMS velocity divided by 3 times kf. So that is very close to the actual turbulent diffusivity. And this time scale is longer than the turbulent turnover time by a factor which has to do with the scale separation ratio squared. So it's almost 700 times longer. And we, in order to see things more clearly, we average over the y direction, which is the direction in which the field, the imposed field points. And we also average over slices in time, 18 turnover times. TO means turnover time.
K1 is the inverse box size. K1 is
the box wave number, yeah.
So it's a time you need to diffuse from forcing scale to the box scale.
Yes, exactly, yes. Turbulent. Good. So now I will show you the movie. And I will stop this here. So turbulent, time is already here now 900 in turnover times. This is the By, and By in the imposed field was here 0.005. So this is twice as, so this was the value of the imposed field, and this is the color scale. Here's the low density at the top, higher density at the bottom. And here's what we see then as time goes up, continues going on. You see the accumulation of much magnetic flux in one particular part of the box near the top part of the domain, and reduced flux at another position. So we have a large-scale structure now. The question now is, where does it come from? In order to measure, so let me show there was nothing in the beginning, and there's actually some structure coming quite quickly, but initially there was zero magnetic field, zero magnetic perturbation. All the magnetic field was generated by the tangling of this imposed field. So now the question is what is happening? One of the ways of quantifying now this picture is by taking a Fourier transform of the magnetic field in this x direction. This is x direction. And then we should see a sine wave at the wave number 1. So we record this amplitude B1 in the following. Yes, before I go to that, the image on the three-dimensional box to show you that if you don't average and you look at any time, not just averaging over a few time slices, there's a lot of small-scale structure going on, but you don't really clearly see a large-scale structure. You do see a little bit of more white over here and a little bit more bluish over there, but it's not a clear signal in this case. It's a long movie. So here's shown is a sequence of different runs with different values of the imposed field strengths. This is the one. This is the run I showed you the movie of earlier, and here's runs with stronger fields. And the clearest structure we can see in particularly this run, and the structures become less clear, although there's some vertical segregation here in this case. They become less clear for either weaker field or stronger field. And here is shown this quantitatively as the imposed field in units of the equidistant field at the average, for the average density is concerned. This is at a fairly small field strength of approximately 5%. However, with respect to the local equidistant field strengths near the surface, it's more like 15% is the field strength where the signal becomes optimal or strongest. 15%. Now I look at the magnetic Reynolds number dependence. So, top here. As a function of magnetic Reynolds number, here's the magnetic Reynolds number. And remember, it's defined with respect to eta and the wave number at the forcing scale. That's my magnetic Reynolds number. If this is smaller than 1, you don't see large-scale structural formation at all. And if it's bigger than 1, you do see structural formation at the value of about a little bit less than 4%. And it's perhaps independent of Rn. Let me also remind you that the Reynolds number is defined with respect to Kf. So if people calculate the Reynolds number with respect to the full box, then it will be bigger by a factor of approximately 100. So it will then be 7,000. Just to illustrate that 70 is not that small a Reynolds number as it might sound. Here is then shown the simulation at a smaller Reynolds number, and you see quite a dramatic effect, which you, and I'll show you that later too, which you also see at higher scale separation. So what is going on here? So we see is, here's the same thing shown at a larger scale separation, 30 instead of 50, and now it's a 256 cube simulation, again running for a long time. Again, no structure in the beginning, and then all of a sudden a very strong structure, and it actually sinks down. So what is this? It's a large-scale structure which then even sinks down. So here is the tentative explanation for this. We are looking for a turbulence effect. So let's look at the total stress that we have. The total stress is on the small scales at least, something which might be isotropic. So if you isotropize this expression, then you get 1/3 times delta ij times u squared. From this one you get minus 1/3 delta ij b squared, but from this you get 3/2. So altogether you get plus 1/2. So what you see is that the magnetic field enters the total stress with a smaller contribution, with a smaller factor. And if you assume that the total energy, kinetic plus magnetic energy, is approximately constant, then you clearly see that the effect of a magnetic field is a decrease of the effective turbulent pressure. And so that is what we believe is actually going on. So you have turbulence. The turbulence adds to the total pressure by turbulence pressure, by producing turbulence pressure. There's gas pressure. There's also the magnetic pressure from the imposed field, but there's turbulence pressure. And now this magnetic field that we impose, if it gets stronger in some place, it reduces the turbulence pressure. The question is now by how much? But it can reduce the turbulence pressure. That's why we will be talking about a negative effective magnetic pressure effect, and later about instability.
But why should be isotropic if you have a stratification and you impose the magnetic field in one direction?
It will then not be fully isotropic, but if you were to calculate the isotropic part, you will find an even stronger effect, because you have then this one will dominate under anisotropic conditions over this one, and it has an even stronger contribution with a minus sign. So anisotropic effects can make this effect even stronger. But really what counts at the end is that the simulations actually do show a structure. But I can then also calculate the, before I come to that, let me show you here how it looks like in bigger boxes, wider boxes. Here is shown without time averages. Here is shown with time averages, and you clearly see as the box becomes longer, you have a typical wave number or wavelengths of the instability in the usual fashion. So here's what we will be looking at now quantitatively. We will be looking, it's sort of a similar language to mean field dynamo theory, which we will not be doing. In mean field dynamo theory, one is looking at U cross B. Here we are looking at UI, Uj, the Reynolds stress. And of course, normally people who do LES, for example, they parameterize the Reynolds stress in terms of just the mean flow, which of course is certainly a valid contribution that gives us turbulent viscosity. But there will be other contributions, and as this will not cover all of them, but some of them might have to do with this reduction of the effective magnetic pressure. And this will be quantified by a quantity that we will be calling QP. It's like the alpha effect of the Reynolds stress. So it's called QP, P for pressure, as opposed to this tension strain, which would be another contribution. And now we will be looking at trying to calculate this contribution. Let us first look at a box which has nothing to do with stratification. So it's an unstratified box with an imposed magnetic field. The imposed field strength is increased here from the left to the right. And we see that the magnetic energy increases, the turbulent kinetic energy decreases, and the sum of the two is approximately constant, but it's not quite constant. So to a good approximation, this remains constant, and the overall effect of the imposed magnetic field is a suppression of the Reynolds stress, or the isotropic part of the Reynolds stress. And this is shown here quantitatively by measuring the quantity QP, which I introduced before. So QP is getting small for large field strengths, but it's getting bigger and bigger and bigger for weaker fields. And it's actually getting much, much bigger than 1. The quantity that really matters is Q relative to 1, so QP minus 1 will be the quantity that determines the total pressure. There has been a work on this for quite some time actually, but it has never been realized that it might have actually applications to forming an instability. So the suppression of the Reynolds stress was calculated with having in mind, of course, calculations of alpha quenching. Keith Mossad might have also done this before that. So people looked at, of course, the Reynolds stress in order to calculate the effect on the alpha effect, the effect of the magnetic field on alpha. That's why people like Ritter and Rüdiger calculated this. What Rüdiger found is that only for magnetic numbers less than 8 can you have a suppression of the turbulence pressure. But all these theories were done with first order smoothing and are only valid for Reynolds numbers bigger than 1, smaller than 1. So keep in mind, because I showed you the Reynolds number dependence. Rüdiger later found that that the Maxwell tension might actually formally become negative, but only when the theory becomes invalid. So clearly that was not believable, or was also not believed at the time. More recently, again here, Rüdiger and company have results on this for Reynolds numbers smaller than 1. And they don't find, in this case, an effective magnetic pressure, but they do find a suppression of the tension. Then there's a series of different papers by Kleorin and Dvorachevsky who have calculated this effect and have actually already suggested in their early 1990 paper, and then in subsequent papers, that you might have such an instability which could lead to the formation of flux concentrations. And that's really what we seem to find here. Here is now shown a mean field calculation where we basically solve the averaged equations using parametrizations for the effective magnetic pressure. And what we see here is the formation of an instability with a characteristic wave number, and you see structures which fall down. So why do structures fall down? that can be understood because if you have a negative pressure, the negative pressure adds to the, in order to have pressure equilibrium, you have to have a bigger gas pressure, and therefore having more density, and therefore the structures must become heavier. So here's now how we can calculate this QP function, not for unstratified runs, but now for a stratified run, where you can get the whole curve much more cheaply in just one run. So what you do is you calculate QP at every different height for a given imposed field strength. You get a characteristic curve like this. Then you can calculate 1 minus QP, which is the effective magnetic pressure, 1 from if there was no turbulence effect, and then you add the turbulence effect, which adds negatively. And you get, again, QP as a function of height. But now, because at each height, B equipartition changes. The imposed field is approximately constant, but B equipartition is dependent on height. And therefore, this at every depth corresponds to a certain value of the ratio B over B equipartition. And so by simply re-expressing this coordinate here in terms of the B field, you can directly get the effective magnetic pressure. And it agrees with the curve that we had before. If I show you the curve before, one of the curves before was shown here. Here, this was done for the unstratified runs, and there we had to do different simulations to get one data point. But now we can get this full curve actually for just one run. You see the instability. The same has been done for convection. Now convection is quite different in some sense because it's now all of a sudden unstably stratified. So it's no longer isothermal, it's unstably stratified, the entropy, the specific entropy is decreasing, and the turbulence is not driven by a forcing function. And still you find a negative effective magnetic pressure, which is even relatively strong in this case. Here you see these curves for different Reynolds numbers now. These are only the smaller end of the Reynolds numbers, but what we clearly see is that for Reynolds numbers of about 1.7, this minimum disappears. So you really need magnetic Reynolds numbers bigger than 1, which is exactly the limit when first order smoothing is no longer applicable. One question, of course, is how can you parameterize these curves? The tentative formulation of these can be done by assuming a simple fit formula for the effective magnetic pressure. This is, of course, the ansatz that I used all along. But here is a fit formula. It's a simple Lorentzian quenching function. And now we can calculate the amplitude up here and the scaling factor beta p up here. And you find that beta p is approximately inversely proportional to the Reynolds number. So if you compensate this with the Reynolds number, it's approximately constant for these small Reynolds numbers. And this multiplied by QP squared is also approximately constant. So that is the approximate scaling rate that we find so far. Oh, what we also see is here the growth. If you look at the quantity B1 that I introduced earlier, it grows approximately exponentially at early times. But the time scale is exactly this eta t naught time scale, which is a turbulent diffusive time scale, which means several thousand turnover times. So it's a long time scale. Whereas the RMS field of the background stays approximately put, and that grows much, much more quickly. After approximately 20 turnover times, you have reached a steady state. So it's a very slow process. So if anybody does such a simulation and runs not long enough, you will not see that. Tentatively, we apply and might want to apply it, at least in future, to explaining sunspots. People often assume that a sunspot is a consequence of a thin magnetic flux tube at the bottom of the convection zone, which it would be very strong. People are hypothesizing that it's very strong, 100 kilogauss, which is hard to understand theoretically because it's much, much stronger than the equivalent value. So therefore, I have a very hard time accepting such a claim. Furthermore, it's very hard to imagine that these tubes remain coherent during their ascent over so many pressure scale heights from the bottom to the top. There's 200 pressure scale heights. Instead, what you might have is sunspot formation, or at least active region formation locally, near the surface. by a mechanism that is related to this or at least triggered by this. And that is not necessarily that absurd, it's just unfamiliar to many theorists, but observers have often an easier time accepting such a somewhat revolutionary claim here. So I would conclude then and would like to point out that this latest has been published in an update letter. Let me also remind you that this effect really does not exist below Rm of 1. It's a large Reynolds number effect, although we have not yet had access or positive identification at really very large Reynolds numbers. It becomes very difficult because you have to run for such a long time. But clearly what we have seen is that the effect becomes more pronounced at larger scale separation. In the case of the Sun, we might really have a lot of scale separation available. Sun's photoactive regions have the size of over 100 megameters, or they are at least living in a container of a size of about 100 megameters, and the eddy scale to determine eddies is about 1 megameter, so we have a lot of scale separation. So I'm looking forward to seeing what happens with this method, or with this new effect in more realistic applications to the Sun. Thank you.
Questions? I don't understand why it takes so long, why it's this diffusive time.
It's I mean, the question is what's the growth rate of the instability? And if you write down the growth rate, it tends to be one of the instabilities which is the large scale instability, which has a damping term, and that damping is due to turbulence. So that is what brings in the time scale. Then you have a effect which is
KV or something like it.
It is somehow related to the Alvin speed, yes.
Yeah. Makes sense.
Yes, you is any of this throwing new light on the top of the healing of the corona, which is actually the very first research program which I will.
Okay. The healing of the corona is not directly addressed in here. What we believe and what many people are finding is that that Parker's 82 scenario is what really can heat the corona. So these are large-scale magnetic structures, which might be opened up, of course, but if you pack them in a box which is just Cartesian, then you have a magnetic field between two ends, and you are shuffling magnetic field ends around, and you are producing contact discontinuities, which imply a lot of magnetic dissipation. And if you are able to do the work on the magnetic field, this magnetic work will be dissipated into heat or some radiation, which heats the corona, which has been actually obtained in rather realistic simulations by other groups, including Orkenauer himself and other people now in Oslo are doing such simulations routinely, also in Freiburg and Lindau.
There have been so many different theories of this. It's taking back and forth.
Yeah, but so it's most likely not wave healing. And really what does work and quantitatively works correctly well is, so people have done simulations of the surface where they have the artificial velocity fields here, and the vertical component of the magnetic field taken from active regions, and they find arches, which look very much like the arches that you see from the trace satellite. And now you can ask the question, what happens in a direct numerical simulation, or not a real direct simulation, but a simulation where they actually use often hyperviscosity, how much heating do you produce? And the heating that is being produced is sufficient to sustain the cooling that you have in this atmosphere after a time of approximately 15 solar minutes. So quantitatively, these simulations seem to be rather realistic and work out to explain the heating at about 2 million Kelvin.
Could this idea throw some light on the time delay that's existing between the sunspot cycle and the torsional oscillation cycle? That's about 2 years, I guess, something like that.
I think the time delay comes from by looking at what actually drives the torsion oscillation. And the torsion oscillation, we think, is driven by the large-scale magnetic field, which indeed might have, it might be actually a consequence of this effect to some extent as well, in addition to the actual dynamo effect. So it's clearly somewhat early to really look into such a detail at this point, but clearly when we are getting to the point where more realistic models are being produced, one should clearly look at all these different constraints, and there are a number of other constraints. One of the most serious constraints for any solar dynamo theory is, of course, that we know magnetic structures move equatorward, and at least at low latitudes, and not poleward. That's the most serious constraint, and that one is very difficult to obtain, to get right. Often people don't get migration, they don't necessarily get the, and they often get migration to high latitudes. Another thing that is really very different and difficult to get in the sun is, near the surface there's a strong negative shear layer that is also never obtained in any direct simulations yet. Even though it's easily explained away by simply talking about angular momentum conservation, but why don't you get this in the simulations easily out of this? So before you want to really make a direct comparison with the sun, you should get a few other things right, and people are not getting them right. And yet another very big problem is the Taylor-Proudman theorem. According to both direct simulations and also mean field calculations, the contours of angular velocity are still too close to vertical or cylindrical, especially at low latitudes. There's some progress at high latitudes, but really at the equator, there's a lot of differential rotation at the equator. And that explains perhaps why some simulations, so that's how it looks like. So it might become more like this at high latitudes, but in the simulations, the contours of angular velocity are mostly cylindrical. And so you have a lot of shear, which produces a lot of magnetic field in low latitudes, which is more than what is realistic.
Okay, let's send this paper.